Welcome everyone. In this video I'm going to show you a digital potmeter, which is the MCP41100 potentiometer. So as you can see, I don't have too many things on the table right now. So we have this breadboard here, and now I'm using an STM32 circuit, and we have one digital potentiometer here and the other is here. And I will show you all the connections and wirings, so don't worry about that right now, but in a nutshell, we have the SPI connection except the input connected to the two chips. So these chips are connected in a parallel connection to the SPI, except their chip select. So each of these chips have their own chip select pins. The first one is using the default SPI chip select pin for the STM32, and then the second chip right here is just using some random digital pin, so it doesn't matter. And then what we will do here is we will measure the voltage on the wiper of the two digital potentiometers. So that's why I have the two multimeters here. And the potentiometer now is connected between the ground of the STM32 and the plus 3.3 volt. So one potentiometer will go from ground to 3.3 volt. And the other potentiometer will go the other way around, so that will decrease the voltage from 3.3 volt to ground, and you will see it on the screen. So that's the basic configuration here, and I just want to show you how it works. And when I show you the wiring and I talk about the two chips in a bit more detail, you will see how we can send the commands with the microcontroller and so on and so on. So now I just wired this up because I was testing it, of course, to measure the output voltage on the wiper by using two of the AD converter pins of the STM32, but I don't need that right now, so I just removed those cables. And what we have, let's say that the channel 1 is this chip right here, and that is the wiper. So I connect it to this multimeter. So one pin goes to the ground, and then another pin goes to the wiper. And once again, I will show you the wiring, so don't worry about this if you cannot understand it, because I will explain it in very details. And then we also curious about this chip right here. So the ground is the same, of course, but the output of the wiper goes to a different positive pin. So this is what we have right now. So once again, we have the STM32, which sends out the command to the two digital potentiometers, and the left-hand side potentiometer is read by this thing here. And we just simply will read the voltage. And then we have the right-hand side potentiometer here on the breadboard, and that will be read by this guy here. So all I have to do, I have to power up this device. So it's a regular USB connection. So let's see what happens if I give power. So as you can see, this started from 0 and now it goes up, and this started at 3.3 and goes down. So what it does, and I show you the source code, so don't worry, this will go up until the digital value on the SPI connection reaches 255. So that's the 8-bit, the maximum value of the 8-bit. So this goes until that, and this goes the other way around. So one thing is that they should meet somewhere halfway, around 1.65-ish, and you see that they are roughly at there, so they met there. So this goes 0 to 255. So now this is approaching 255 regarding the digital values, and this is approaching 0 regarding the digital values. So you can see that soon this will reach 0, and then the counter will restart. So this jumps back to 3 volts and this jumps back to 0 volts very soon. Let's wait for that. So this should happen at around 3.3 volts and done. So you see this is roughly at 3.3 and this is now at 0. This is now in millivolts, so this is 300 something millivolts. So it's very easy, and you can see, and you will see, that the wiring is not as difficult as it seems here. It's just the long wires. But why I show this to you, because by using a digital potmeter you can do many crazy and many nice things. So if you have an LED light, for example, you can control the brightness of that because you have basically a digital potentiometer. So one thing is that you can do this with PWM, of course, but also by changing the value of a potentiometer, then you can run different amount of current through the LED light, and by that you can play around with its brightness. For starting, I think this will be enough, and now I will just jump to the computer, and first of all I will show you some kind of drawing of this whole thing, and I will explain a few details about the SPI connection and the SPI communication. That is basically one of the most simple things that you can find in these connections and stuff, because you just have to send very few details to the potentiometers. And then I will also show you some small calculations, and finally I will show you the source code. So let's see what is happening inside this STM32 by checking all the small details in the computer. So let's discuss this circuit that I showed you previously. And let's first discuss the integrated circuit. So let's look at this part here. It's an 8-pin or 8-leg microchip, and then we have the SPI pins right here, as you can see, and then we have the VSS and the VDD, and then this is the ground, and this can be anything up to 5.5 volts, but as you could see it, I was using the 3.3 volts because I was using the STM32 and I just did not want to make any mess. So 3.3, and it's also more lucky choice because we only have 8 bits, so 256 different levels, and we get a bit more precision if we divide 3.3 to 256 parts instead of 5 volt. So that's what we have. And then the PB0 here, that is connected to the ground, and this is the Viper, or if it is more easier to see, this is the middle of the potentiometer or the output of it, and PA should be, let's say, VDD. So in that case I was using the 3.3 volt rail. And let's take a look at this resistance calculation. So I want to make this thing more clear, how this potmeter, or how potmeters in general work. But basically what we have here is we have 2 resistors, and then this, let's call this B, let's call this A, and then we have the VDD up here, and we have the G and D down here. So, and then here we have the output, but we call this W as Viper, so it's more easy to relate to the drawing here. And this thing is from the datasheet, and this is for the 10 kilo ohm version, but we have the 100 kilo ohm version, so this is a bit different, but yeah, I will explain everything soon, because this is just an example. So what we have here, and what you can see it in the formula, so if we want to see the resistance between PA and PW, so up here or right here, then that is calculated by this formula. And you can see that we use this RAB, which is this value, so the value of the potentiometer, and in our case that is 100 kilo ohm, and then 256 minus dN, where dN is the actual value of the potentiometer that we gave, like the digital value, which changes between 0 and 255. So we subtract that number from 256, and then we divide by 256, and then we add the RW, which is the resistance of the Viper, and it changes from it changes between the different types. For example, the 100 kilo ohm device has 125 ohm in general. That's the minimum value stated in the datasheet. So that's what we have. And then let's call this in the same way, so RWA. And then we have the second part, which is RWB. And that is more simple, because that is basically gets rid of this 256 minus dN. So instead of that, we just have the dN here, but the rest of the formula is the same. So how you should look at this digital potentiometer is that initially we have something like this, and this is just an abstraction or sort of a illustration, which might help you to better understand this thing. So what we have here, let's start with one single resistor, and then we have the Viper here. And what happens when dN equals 0 is that this part or this term becomes 0 in the equation, and we just have the RW, which is a very negligible 125 ohms. And then up here, this becomes maximized because this dN term is 0. So we have the maximum value here that we can reach, and that is basically 100 kilo ohm times 1 here, if we see it, because yeah, you can just separate this. So this is 100 kilo ohms plus the Viper resistance, which is again 125. So what we have here is, up here we have a very big resistance, and we have a very low resistance down here. So that would mean that in that case, so when dN equals 0, let me write it down, the output voltage would approach towards 0 volt. And let's say we just increase the dN to 1, then this is again an abstraction. What would happen that this thing would, let's say, split up into two resistors. And if you check the values, so we just subtract a very small value from this as compared to the others, and here we multiply this thing with a very small value. So then this still, let's say, a large value, and then the bottom part is a small value. I try to illustrate it like this. And then we have the Viper, I'll just put the W here, and then the power supply and G and D. So by this, we started to change the ratio between the top and the bottom part of this voltage divider because this potentiometer is basically a voltage divider with 2 steps. So step 1, step 2. And then now this will be a bit larger than 0 volt. So then this value would be something like 0.017 if the power supply is of course 3.3 volt. So we stepped away a little bit from 0 volt, and then we move to dn equals 2. So this becomes even larger, and what you have by doing this like iteratively or progressively, that let's say when the value of the dn is 127, so we are right in the middle, then the 2 resistors are the same. So this is still 3.3. So then this should give us 1.65 volt roughly. And then if we continue and increase this value dn to 256, then you will see that we eliminate this part. So this will be 0. So this term becomes 0, and we just have the Viper resistance, and this part becomes maximized. So if we continue the same logic here, then we will have a very, very small resistance here, and we have a big resistance down here. And we have the Viper, and then here we have the 3.3 volt. And then this would mean that our output voltage at the end should be roughly the same as the power supply voltage. So this is how it works. So you basically just change a digital value, and then you see that you have the 2 parts. So one part between PA, PW, and other part between PW and PB. And as you start to increase the value, the ratio of these 2 things increase. So if you divide the resistance up here by this, then you get smaller and smaller number, because in the beginning this is big number and this is very small number, and as you start to increase the dn, then the value of RWA decreases and this is increasing. So then you have a smaller and smaller number as the ratio of these 2 numbers. And basically that's all. And I hope that this is quite easy to understand, but this is just my approach to better understand how potentiometers in general work as the voltage divider or as a voltage divider, and how we can understand this formula through the voltage dividers. So that's all. So let's check the SPI command first before jumping to the actual wiring or drawing. So what we have here, that's very easy, and you will see it in the source code as well, because after this I show you the source code. So what we have to do is we have to pull the chip select pin to low, and it should be originally high. So it goes high to low, and then we feed in the clock. You have to make sure that you use the mode 1 in the SPI settings, so you will have this kind of clocking. And then our whole thing here is 16 bits, and I don't know if you have noticed here, but we only have 3 pins for the SPI here, because we only send data, and therefore we just use the chip select, the clock, and the slave in pins. So what we have here is we have 8 bits of command byte. So of course 8 bits is 1 byte, but yeah, so we have 1 byte here as the command byte and 1 byte here as the data byte, and we write both of these, or we send these as command. So let's go to this figure 5-2. So what we have to do, the first 2 bits, we don't care about those, so they can be anything. I choose them to be 0. And then we have the most important part, the command bits. And we have to look at this part, what happens. So if we want to write data, then C1 should be 0 and C0 should be 1. So that's what we have here. And if you change it to different values, then you send a different command. So if it's the opposite, so C1 equals 1 and C0 equals 0, then we shut down the potentiometer. But I don't care about that, so I don't use this. So just let me do this. And then we still have a few bits here. So the next 2 bits are don't care bits. So either we send 2 1 or 2 zeros, it doesn't really matter. And then finally we have the potentiometer selection bits, but I'm using the MCP41100, which means that this single chip here is just one potentiometer, so we are just sending 2 zeros or whatever we send. It will not be executed because we just have one potentiometer. So yeah, you will see the code and you will see what I sent there. And then we have to write the data. And this is very simple because the Arduino code or the library will do everything for you. So we here have an 8-bit or 1 byte data, of course. So if I just go down here, so of course 8 bits because of this. So we have 256 different levels, and you just change these numbers. But what you do at the end of the day, you just have a decimal number between 256 and 0, or 255 and 0, sorry. And that's how you use this. So for example, you just, this is again just an illustration, so you send an SPI command, which you write 73. And then that 73 will be actually written in this equation. It will be substituted here, and you will get some sort of resistance and some sort of voltage drop on the output of the potentiometer. So it works very easily. So basically that's all regarding the SPI command, and you will see that it's crazy simple. One more thing that you have to think about is that when you finished sending the command to the potentiometer, you have to bring back the chip select pin from low to high. And then until the following command, it should stay high. And that's very easy because you just use the digital write command, and then that's all. So regarding the drawing, so as I said, I will be using the STM32 for this project, or I was using already. So we have the 3 SPI pins for this particular microcontroller, and you will see that in the source code, so I don't bother spending too much time. But what we have is basically the chip select is the A4, and then we have the A5 as the clock, and then we have the A7 as the master out slave in. So what you see here is everything goes to the first chip here. So let's call this 1 and let's call this 2. So the first pin, as you see it up here, so that's the chip select, that's done. The next one is the clock, that's done, so that's the blue wire. And then we have the slave in or master out, so MOSI, and that goes to the third pin. So this is done. And then you see that the fourth pin is connected to the ground here, so that's also done. And then let's jump to the second pin. So you can see that I connected these two things parallel regarding the SPI connections, except the chip select, of course, because that has to go to a different pin. But you have total freedom here because you just have to choose a leg from the STM32 which you want to use for switching between high and low state. So here I used the B9, but again you will see this in the source code. So that will be our chip select pin. Let's call it chip select 2. So that goes there. So that's again done. The clock is parallelly connected to this, so we have the SCK here, and then down here the orange one is the SI, and then again this goes to the G and D, as you can see. Let's jump to the other side of the pin, or the other side of the microchip. So we have the plus 3.3 volts, so that's the VDD, and that applies for both sides. And then we have the PB0, which is connected to the ground. And then this is a bit strange, because if you see it from a certain perspective, this should be the PA. For example, if you look at this drawing, the PA is above the Viper, and here the PB is above the Viper. So it's a bit counterintuitive, but still. But I notice it here as well, that this is the PB pin, PB0. And then this, I drew it a bit higher because I want to show you something. This is the Viper, and then down here this guy is the PA. And the same applies here. And why I have this, so this is green and this is blue for a reason, because what I will do with the source code demonstration is that I will read the output of these pins with the built-in 12-bit AD converter of the STM32. So the green will be obviously connected to the green leg, and the blue will be connected to the blue leg, and you will see how it works. So what I want to see and what I want to show you is exactly this thing with the changing resistors. So you will see that basically the sum of the two values will be constant. So we will be receiving roughly 100,000 ohms all the time, but what will be different is that the ratio between these two resistors. So as this value will increase, this value will decrease, and so on. And I show you both of these things. What I will show you in the source code is the same as I showed you in the demonstration. So one microchip or one potentiometer will decrease its resistance, and the other will increase its resistance. So basically that's what we have. And also I will print the RWA and RWB values for both chips here. So you will see how it is calculated. So one thing is I will not print the voltage here, but I will just print the raw value, and you will see how it works. So I think I explained everything here, what I wanted. So let's just jump to the Arduino code, and then you will see what I'm talking about. So this is the code, and it's very, very, very simple. So we just need the SPI, and once again I'm using the Arduino IDE, but I'm using the STM32 microcontroller, and I'm using this STM32 Arduino core, which allows us to have a Arduino based program on this STM32 microcontroller. So this makes our life very easy, but since I'm using the Arduino code, this whole code is valid for Arduino as well. The only thing that you have to change is the definition of the pins, because now I had to define the pins as they are defined for the STM32. So I refer to the pin number in a different way, but you can Google this, and you can just redefine the pins, and you can use this easily on Arduino without any modification except the pin numbers. So let's jump back to the beginning of the code. So we add the SPI library, of course, because we have the SPI based potentiometers. And then what I have here, it doesn't really need any explanation, but so I just have the analog value, which is the output value of the AD converter, and then I define the two pins for the AD converters, and then the two chip select pins. So this one here is the regular SPI pin, so that is like the default pin, and this is my randomly chosen pin for the other chip. And then here what I have is the RWA for the chip number 1 and chip number 2, and also I repeat the same for the RWB. And then, as I said, one potentiometer will increase its value, so that's why it starts from 0, and the other will decrease its value, so we start from the top, so they will meet halfway, and then one will reach 0 after a while and the other will reach 256. So the setup is very simple. So this is just for the serial port. You will see how this gets printed. We have to define both chip select pins as output pins, of course, because we want to switch the potentiometers with them. And we also make sure that we pull them up to high level, because whenever we want to write these chips, we have to go low with the chip select pins. And then we have to start the SPI. So that's quite simple so far. And what we do, again, I follow the same practice. So I try to simplify my loop as much as possible. So I just insert the functions, and then I do the main part of the work inside the functions. So this is very self-explanatory. So you can see that I write some certain value on the potentiometers, and then I just wait a little bit, and then I read both analog pins, and after that I increase and decrease the value of the potmeters. And here you can see that I just basically reset the values of these potentiometers after they reach the maximum and let's say minimum values. So how do we write the potentiometer? And this is the chart what I was explaining to you in the previous slide or picture. So as the timing diagram says, we have to pull down the chip select pin to low. So this is the first chip, so that's why we have this one marker here. So we send the 8-bit command here, and you can see it's very simple. This is in decimal 17, but you can see that this is the full binary number, and I just divided it up to the sub commands. So you can see what are the don't care bytes and what are the actual commands. So this should be fairly simple. And then I just wait a little bit here. So we send this value to the potentiometer, and then we send an actual value which is created here. So of course, first when this starts for the first time, then it uses this value. So it starts with 0 for the potentiometer 1, and it starts with 256 for the potentiometer 2 when we go to this number and of course this number. And then this is done. So we increase the value and decrease the value. So the next time this will be updated accordingly. And you can see that here we are just putting a simple integer, which is a decimal number. So we don't necessarily have to go with hexadecimal numbers. And what I do, I just wait a little bit to avoid any confusions, and I further introduce some delay by printing something on the serial. So I just want to keep track of the numbers, and I want to show you this. So we see that we will print the value of the counter 1, and that is here. And we have to switch back to high regarding the chip select pin. So then the microcontroller will set the pin to high, and then the potentiometer will know that no more command is expected now because the chip select pin is high. So I don't repeat it, but the potentiometer 2 works in the same way, but we will write a different number here. And then read analog pin. This is again very easy. So we fill in the variable here with the value of the analog input pin 1, and then I print it so I can keep track of it. And these are the formulas which I was explaining to you. So this is the first chip's RWA and RWB values, and we have these printed on the serial port. And I always print the sum of this, because as I said, the sum of this should give you the resistor value basically. So if we are talking about a 100 kilo ohm potentiometer, then this should be always 100 kilo ohm, and what we should see changing is the RWA and the RWB. So their ratio will change, and therefore the output voltage on the Viper will change. And the same practice for the analog pin 2. So this is all. And then I just kept some small comment here that I should know that for this particular device, for the 100 kilo ohm device, the RW is 125. And here, if you have noticed, I'm using, so you have to be careful if you do this calculation yourself, that the formula is given in ohms. So when you write in the resistance of your device, and for example you have a 100 kilo ohm potentiometer, then that is 100,000 ohms. So here you have to write 100,000, otherwise you don't get the perfect numbers back. So what I'm doing now, let me start the serial monitor, and then let me connect the device. So let me start again. So you can see that of course it's not too easy to follow it, but I will try to resize it properly. Luckily these numbers or these things are not jumping. So what you can see is that for example here the sum is always the same, and that is the sum of the RWA and RWB. And as you can see, these two numbers, so this guy here is increasing and this guy here is decreasing. And this is how the ratio of the two resistors in this voltage divider changing, and this is how the potentiometer will change the output value. And as you can see, so the analog 2, you can see it here, that is now decreasing as RWA is increasing and this is decreasing, and that's what we would expect. So as we increase the value of the resistor in the top of the voltage divider, then the output voltage will decrease, and this will reset soon. So let's wait for that. So you see, so now we have a very high output there because the bottom resistor is very high and the top resistor is very low in the voltage divider. So in that case we would expect of course low values. And if we check the 1, so in that case the output is increasing, so maybe it's more easy for you to follow it. So what you can see how it is increasing is that the top resistor in the voltage divider is getting smaller and smaller, and the bottom value is getting larger and larger. So what you do is that you constantly decrease the ratio. So RWA divided by RWB is getting smaller and smaller, and that's how you get larger and larger output value. So I hope that this is clear. And down here, or yeah, anywhere where you see the counter, you can see how they behave. So you see the counter 1 is increasing and the counter 2 is decreasing. And this is basically all. So in this video we could learn how this SPI based digital potentiometer works, and you could see, and you can still see, that it works very nicely and very smoothly, and the voltage values or the resistor values are changing in a very nice way. So if you have some certain low and stable voltage source for this kind of potentiometer, then you can divide that voltage into very small sub steps. So that's very nice. So what I will do in the next step with this kind of circuit and the things that we learned here is I will build a digital power supply. It will be just a single channel power supply, but what we will able to do is we will be able to change the voltage and the current on that power supply by using this STM32 circuit with these two digital potentiometer circuits. So that will be very fancy, but we don't stop there. So since it's a power supply, we will need the output voltage and the current. So I will measure the current and the output voltage also by using this circuit, and I will also add the display, so we will see it, and it can be a standalone device, and we don't need the serial connection to that. So in the next video, which will be related to this circuit, I will show you how to build a digital power supply based on a DC-DC converter. So in reality, it's not really a power supply, but it's more like a voltage or current regulator, which has to be connected to another real power supply. But if you do the full circuit, then that will be a power supply. And basically that's all. So I hope that this kind of teaser will keep you interested in these kind of projects. And then you will follow up with this power supply that I will build very, very soon. So I hope you liked this video. I hope you learned something from this. If you have some questions, just please ask me in the comment section. I'm glad to help, and I also read all the comments and I try to react or reply to those which have some specific questions. And please don't forget to subscribe if you haven't done it already. It helps me a lot. So this was all, and we will build the power supply in the next video. So see you in the next video.